All right, so you've been diving into orthonormal bases
Hmm.
and how they work within vector spaces. And get ready, because we're about to break it all down. Uncover some of those aha moments.
Yeah, it's really interesting stuff. And although it can seem kind of abstract at first, these concepts are really foundational in a lot of areas.
Yeah, okay. So let's start with the basics. We've got this definition of an orthonormal basis as a set of vectors that are both orthogonal and normalized. But what does that actually mean?
Okay, so imagine a perfectly aligned grid, like the kind you'd see on graph paper. Each line on that grid could represent a vector in your orthonormal basis. So they're all perpendicular to each other, hence ortho, and each line is the same unit length. That's the normal part.
Right, so it's like this, perfectly organized scaffolding for your vector space.
Exactly.
And just like you'd use, coordinates on a map to pinpoint a location, we can use an orthonormal basis to pinpoint any vector within that space.
That's a great analogy. And what's really powerful is that any vector can be expressed as a unique combination of those basis vectors.
Wow.
So it's like having a universal language to describe any point or direction within that space.
I'm looking at this equation here, showing how we can represent any vector using the basis vectors. And it seems like we're basically just breaking it down into its fundamental components.
Yeah, that's a great way to think about it.
Yeah.
You can kind of think about it like mixing colors. Your basis vectors are like your primary colors, and the coefficients in that equation tell you exactly how much of each color to mix to create your desired vector.
Right. And to find those exact amounts, those coefficients, we use this inner product trick, which almost seems like magic.
It is pretty elegant, yeah. The inner product essentially lets us isolate the contribution of each individual basis vector. It's like having this filter that sifts through everything and picks out only the component of your vector that aligns with a specific basis vector.
So that makes that equation a lot less intimidating.
Mm.
What makes the inner product so important here? Why is that like the go-to method?
Okay, well, the beauty of the inner product is that it exploits the orthogonality of our basis vectors.
Right.
So because they're all perpendicular to each other, the inner product acts like a sieve, allowing us to cleanly separate out the contributions of each basis vector.
Now, there's also this idea of duality that we see popping up. We're introduced to this notation, the bracket notation, right?
Yes.
With the bra representing the dual vector. And it seems like it's related to our original vector. But how are they different?
Yeah, so duality kind of gives us another perspective on vectors. Think of the cat as a column vector and the bra as its row vector counterpart.
Gotcha.
They contain the same information, but are expressed in different forms.
I see. So it's like having two different, but equally valid ways of representing the same information. Why is this duality concept so useful?
Okay, so it allows us to perform operations and calculations more efficiently. Imagine trying to multiply a column vector by a row vector directly. It wouldn't work, right?
Right.
So duality allows us to seamlessly switch between these representations, making calculations involving vectors and their components much smoother.
Okay, I'm starting to see how all of this kind of fits into this bigger picture.
Yeah.
So we've got this powerful framework using orthonormal bases to represent vectors. And duality gives us these different lenses to view and work with them. What happens when we switch to a different orthonormal basis?
Well, that's where things get even more interesting.
Yep.
So the same vector will actually have different coefficients, depending on the basis that you choose.
Right.
So understanding how these representations transform as we change bases really helps us to grasp the deeper geometric and algebraic structure of that vector space.
It's like you're looking at the same object from different angles.
Yeah.
And getting a more complete understanding of its shape. This has been really fascinating. I feel like I have a much better grasp on orthonormal bases now and their importance in vector spaces.
Yeah, absolutely. And this is really just the beginning. There's so much more to explore within this framework.
Awesome. Well, thanks for joining us on this deep dive. Keep those brains buzzing.
Absolutely.